Hello world, it's Rational Pi, and I'm back with you today for the 11th episode of our AI series. Due to the code taking a little bit longer than I expected, it's probably going to be another couple weeks until I'm done, so I'm probably going to start a new project next week. I haven't entirely decided what that's going to be, so I'm going to take the next week to try to figure out what I'm going to do, and something that I hope you guys will be interested in. Before I do the code of the A-star, I wanted to go through one more handwritten, well, not handwritten, but using Excel, method, and we're going to use our actual network that we developed over the last several episodes. We're actually going to use actual data using the longitude and latitude and the heuristic that we came up with ourselves. So everything we're doing now is something that we've already done. We're just going to kind of put it all together, and we'll show you how to do the A-star algorithm. So I'm going to kind of give you guys a hint of what's going to happen. We're going to try to go from node 1, which is Portland, all the way down to node 17, which is Miami. And we're going to do that by establishing what the first node is. So go to the node, set the new total path cost, which in this case is going to be 0 since we haven't gone anywhere. Reestablish previous node, which there isn't one since we're on the first node. Establish new frontier additions. What the frontier is basically nodes that we can access through our current node but have not explored yet. So let's determine what the frontier is going to be. And we based our network based on the top 5 path costs from our previous episode. So the frontier is going to be 23754, which is basically all of those California cities. Oh, come on, where's that? There it is. It's right here. 23754. So right here, and then these 4. And then what we're going to do, we're going to determine what the smallest one is, and that's going to be our next node. But let's go ahead and go through our list here. Compare new frontier additions to previous frontier. We don't have to do that. Establish projected new path costs for new frontier additions, which we don't have to do because they're 0 all the originals. Remove duplicate frontier nodes. Remove the higher path costs. That's going to come into effect later on. Determine the shortest frontier path, which is to node 2, and then go to that node. Okay, so we start at 1, determine that node 2 is the closest one based on geography and the heuristic we determined. So then we go to node 2. So the total path cost is just the cost from 1 to 2. Simple. So then we determine the previous node was 1, that's what we just came from. And then what we did was 1 and 2 basically have the same common nodes that are in their frontier. And if you add the cost from 2 to whatever, it's going to end up being higher than it was from going from 1 to 3. So like this, for example, is from path 1 to path 3. Path 2 to path 3 is going to end up equaling the total path cost so far plus the amount it takes to go from 2 to 3, which is 12. So then it's actually 23.09, which is way bigger than 14.99. That's why whenever we establish our frontier, if we want to go to node 3, we'll just go straight from node 1 to node 3 rather than go from, it's actually node 1 to node 2 to node 3. So we're just going to delete that, and I've assumed all of that whenever I've determined all of our frontiers moving forward. I've already done the work with that, but I just wanted to give a good example of what that ends up showing. Instead of going from 1, 2, 3, it's obviously a lot easier if you go straight from 1, 2, 3. And whenever we have something like going from 1, 4, 8, 7 to 1, 4, 5, 7, we just determine which one's longer and then we delete it because that's not a viable course. If we want to get to node 7, we'd rather take the simplest way there. So then we determine that the path from 1 to 3 is end up being the shortest path, because we have nothing new to add to the frontier, and we go to 3, or we go back to node 1. This is just an example here of going back to node 1. Theoretically, I didn't have to do this. I could have just gone straight to node 3 and just say the previous node was 1. But I did want to show you what actually ends up happening is that once you determine that going backwards is the proper thing to do, you end up going back to node 1 and then going from 1 to 3. I end up dumping that after the first couple examples, but I do want to show you that here. So let's go ahead and scoot on a little bit. Here's where I was talking about with Utah being the link between the west part of the country and the east part of the country. Because what's ends up happening is eventually you have to go through node 8. But the fastest way to do that, we find, is to go from nodes 1 to 7 to 8, which ends up making a lot of sense. Because 1 to 7 is a direct path, 7 to 8 is closer than 6 to 8, so obviously that's going to be the easiest path to go. After you get to node 8 though, things get a little bit hairy. As you can see, every node that we go to east of node 8 ends up having a lot more of a frontier to add, because none of those nodes had been touched previously. Obviously there's not going to be any nodes from this side of the country that's going to directly be closer to any nodes from this side of the country. So Utah's kind of that bottleneck that all of these teams over here, if we want to go from one team over here to one team over here, that eventually have to go through node 8. So this is where things really start expanding and our frontier really starts getting bigger. And we're going to keep going down until, you can tell here, we go from 1, 7, 8, 30, 27, and then that ends up being the shortest one. We have to keep analyzing, keep analyzing, keep analyzing until we find the one that's going to get us to our goal node. Our goal node shows up for the first time here, way down here near the bottom after 30 iterations of this algorithm here. And we also find out that there's only one path to get to node 17, and that's through node 16. So we already know essentially the path that we need to take to get to our goal node, but we have to keep doing this because the algorithm's not going to be satisfied until this is going to end up being the shortest path. So then you keep plugging through until you get to where eventually the goal path is actually the only path left in the frontier. It's the only one that's viable from the nodes that we've already analyzed. So, and then it does one more go around, and then we determine that we found the goal. The total path cost is 86.816 degrees, and we go through node 16. And that's what we end up showing here. So we go from 1, 7, 8, 10, 13 to 16, 17, which makes a whole lot of sense because, I mean, it's about as straight of a line as you can get going from 1 to 17. So now we can do this sort of thing for any node to any node. I thought about doing another example going from node 5 to node 23. That would have been really complicated, especially with all this mess over here. It ended up being over 50 steps, so I went ahead and just did this example so we can get a good example out of the way. And that way you guys kind of see how the A-star algorithm is going to work on the back end. Now on the front end, we're actually using the code. It's a little bit more complicated than what it may show here, but I am working on it. I'm going to be making a video of it as soon as I'm done. I hope you guys have enjoyed the series so far. I'm going to go ahead and suspend it until I'm done with the code. And like and subscribe is always appreciated. If you have any questions, concerns, or anything, or you want more of an explanation of the A-star method or any other search algorithms, please do leave a comment below. And I'll see you guys in the next video.